All right, so last thing I wanted to do was talk about a couple of things to think about for next time. So we've seen this interesting difference between axial and equatorial substituents in terms of energy so far. So we've seen that axial substituents are often more unstable than equatorial substituents, and we've seen how that influences the conformational dynamics of polysubstituted cyclohexanes just on the last slide. But something I want you to think about for next time is the stereochemistry of these disubstituted cyclohexanes. So what you're looking at here are chair drawings on the left and two-dimensional line angle drawings on the right of cyclohexanes, tert-butyl cyclohexanes. And ask yourself, what's the stereochemical relationship between those two molecules? There's definitely a difference between them. So they're not the same molecule, but they have all the same connectivity. So based on what we learned about stereoisomers, we would call those stereoisomers for sure. Ask yourself, are they superimposable? Are they mirror images of one another? And then you'll come to a conclusion about their stereoisomeric relationship. And do the same for this pair of molecules down here. So what you're looking at down here are again tert-butyl cyclohexanols. But on the left-hand case here, we see we have an axial OH sort of to the left of the tert-butyl group. Whereas in this case, we have an axial OH to the right of the tert-butyl group. Think about what the relationship might be between those two molecules. And here again, you can see some line angle drawings in 2 dimensions of those guys there. And the last thing I'll say is that you should get used to translating 2-dimensional drawings of the cyclohexanes, like those shown here, into 3-dimensional representations. Because oftentimes, you'll see that the 3-dimensional representation, the chair form, is crucial to understanding something about the reactivity of a cyclohexane. So we'll see examples in Chapter 4 where reactivity is dictated by molecular shape. And to the extent that the cyclohexanes are constrained by their molecular shape, by the fact that substituents often prefer to be axial or equatorial, we'll see some restrictions of and control of reactivity based on that stereochemistry. So some interesting things to think about there, but that's why we teach and push so hard for you to understand the chair form and how to draw it and what it means, because it can actually have a profound effect on reactivity. So that's actually all I have for you today. Next time we'll take a deeper look at this stereochemistry, and we may move on to Chapter 4, which is an introduction to the fundamentals of organic chemical reactivity. But if there are no more questions, I can stick around for a few minutes at the end if you have questions. But without any more questions, that's all I've got for you today. Thanks for joining us, and I'll see you next time.